Hi guys, welcome back. Today we're going to have a quick look at the trapezoidal rule, and that's going to be for a little introduction into Simpson's rule. So the trapezoidal rule is a method for approximating the area under a curve. So let's say we had this curve here, and let's just call this our function of x. And we know that this is a function, but it might not have a very nice value. So this could be modeling, for example, the side of a hill or maybe the outline of a map or something like that. And so we can't just integrate it using traditional techniques. So we're going to have to find some sort of alternative method. So what we could then do is we could actually, we could treat this in a couple of different ways. One of the ways that we could treat this is we could break this up into evenly spaced rectangles, right? And if we had a look at these rectangles, we could easily find the height of these rectangles, because the height of these rectangles would be equal to the value of the function at that particular point. So this would be x0, f of x0 here. So that f of x0 value, that would be equal to my height. And I could multiply that by the width of each of these strips. And the width of each of these strips is going to be equal to the distance between the points I'm interested in, so between A and B, divided by how many strips that I have. But if I do this method, you can see there's quite a bit of error that's going to be associated with this. So the trapezoidal rule actually gets around this. Rather than treating these as rectangles, it treats these as trapezoids. Okay, so how do we find the area of a trapezoid now? It's not just going to be length times width. So the area of a trapezoid is equal to a half of the height times by A plus B. So if I had a trapezoid that looks something like this, this would be my perpendicular height. This here would be my value, this top value would be my value for A, and this bottom value here would be my value for B. And so all we've done is we've just turned that trapezoid onto its side. So our height here will be equal to the width. This value, this length along here, is going to be equivalent to our A. So what's this going to be? Well, this is going to be our f of x0, isn't it? So this point here, our value for B, so this B here, I've used too many A's and B's. I should have picked some different letters here. I apologize. So this value, or this length along here, is going to be f of x1. Okay, so that would be equivalent to the height of this point here. So let's substitute those values now into our equation for this trapezoid. So this is going to be equal to a half of the height, which is now our width, multiplied by f of x0 plus f of x1. So then we would do the same thing. So again, I don't want this to be a rectangle. I want this to be a trapezoid. I have a feeling if I try, hold on one sec. Let me fix this. There we go. So let's find the area of this second trapezoid now. So this is my first one. So my second trapezoid is going to be half of the height, which is again going to be equal to W. And that's going to be for f of x1 plus f of x2. So let's pop this in our formula, f of x1 plus f of x2. Then we want to find the area of our last trapezoid here. So this one is still looking pretty rectangular, to be honest with you, but that's all right. So let's go ahead and find that area of our third trapezoid now. So that's going to be equal to 1/2 of the width. And this is going to be for f of x2 plus f of x3. So let's write that in there, f of x3. Okay, so let's go ahead and let's add up all these values. So we're trying to approximate the area of A to B of this function here in red. And we're approximating that. So we're going to add up all of these areas. So we end up with a half width of our first function. And I think I'm just going to write f of 1 just to make it a little bit easier rather than having to write f of x0. So what do we need to do next? We've got to add the next trapezium. So that's going to be half width f1 plus f2. And I'm just using f1 and f2 again just to be a little bit lazy here. And then I'm going to add that to my final trapezoid. So it's going to be f2 plus f3. So what I can do now, I can factorize out this 1/2 width, so I end up with the integral of AB for our particular function with respect to x will be approximate to a half of the width. Now, if I was to factorize out each of those, I'd end up with f of x1 plus f of x0 plus f of x1 plus f of x1 plus f of x2 plus f of x2 plus f of x3. So we have single values of our end pieces here. So let's represent this, or these boundary pieces. Let's represent these boundary pieces using B. So B is going to be equal to the sum of our end pieces. Okay. And then each of these middle values, so F1, F1, F2, F2, we have double those values. So why don't we write that as two lots of our middle values, where our middle values are going to be equal to our F1 and our F2. And if we had more of these values, of course, we would include those values as well. So this is where the trapezoidal rule comes from. So we break these functions down into trapezoids, and then we add up all of the trapezoids, and we end up with a half of the width multiplied by the sum of the boundary terms plus two lots of the sum of all the middle terms. So that's where the trapezoid rule comes from. So how does this now relate to Simpson's rule? So Simpson's rule is a little bit different to the trapezoid rule in the sense that rather than breaking each of these strips down into trapezoids, we're going to break these strips down into a polynomial function. And so to do that, we're actually going to need 3 points to create our polynomial function. So now we're going to try and estimate the area of this particular function using our Simpson's rule. And you know what I might actually do? I might write the formula first, and then we'll sort of backtrack, and I'll show you how I got to that point, just because this is going to get crazy and I don't want to lose you at this point here. Okay, so each of these strips, they are also a particular width long, so that width is still going to be equal to the distance between B and A divided by how many strips I have. So this is going to be approximated by W over 3 multiplied by one of our boundary terms, so that's going to be my first value for F and my last value for F, plus two lots of the evens, so that is so that would be this one here, and then I'm going to have 4 lots of my odds, so that would be F3. So I'll go through and I'll explain why, but I just want you to remember that formula. So remembering that B is going to be my boundaries, so my first term and my last term. My evens are going to be all my like every second value, and that would go all the way up to F of 2 minus n. And then my odd terms is going to be my, my starting at my third term, then my fifth term, then my seventh term, and going on all the way until the second or the third to the last term. So this is where I'm warning you that it's going to get a little bit crazy, and I'm going to need, I think, a little bit more space to show you where this function is actually derived from. All right, big breath, here we go. So starting off, we've got this first polynomial function that we're going to describe, and we're going to describe that using a polynomial. So let's call that the area of our first little strip here. So that's going to be equal to ax squared plus bx plus c. So we don't know what that value is just yet, but that doesn't matter because we're just trying to find the general term here. Now, we can integrate this function because we can integrate polynomials really easily. So that's why Simpson's rule works really well. So this area is going to be the integral from, what's this first value here? This first point would be x naught and then f of x naught. So we're going to substitute in that x naught value first. So this will be this value here. And then we're going to go up to this function here. So this is going to be x, this will be x1, so this will be x2, and this will be f of x2. So I need to go ahead, and I think I need to fix up these 3 values down the bottom here once. Okay, so the top limit for that integral will be at x2, and of course we're going to integrate with respect to x. So going ahead and performing that integration now to find this area under this polynomial that we have created, we're going to get ax cubed over 3 plus bx squared over 2 plus cx, and we're looking for the region from x0 to x2. Now, what we can actually do to help simplify these x terms, we can think of this point here, this line, this vertical line traveling through here at x is equal to f1. What we can do is we can treat this as a y-axis. So then the value of x here will be negative w because the width of these strips are all the same. And then the value of this strip is going to be positive w. So I can actually write this as negative w and positive w if we are treating this middle bit here like my y-axis. And I can kind of do this because I'm ignoring these other strips and I'm ignoring all these other strips back here for the minute. So I can do that in this case. So substituting those values in now, we're going to get aw cubed over 3 plus bw squared over 2 plus cw. Take away, oh, I'm running out of space here again already. 1 second. And that's going to be equal to negative aw cubed over 3 plus bw squared over 2. I'm just substituting in negative w to these functions now, minus cw. So let's go ahead and let's simplify that now. So aw cubed over 3 minus negative aw cubed over 3 is going to end up with 2aw cubed over 3. Bw squared over 2 minus, because this is minus bw squared over 2 is just going to be 0. And then cw minus negative cw is going to equal to positive 2cw. So now that I've found the area under the function, let's actually go ahead and let's define the function itself. So just as a little refresh, we've been treating this point here. I'm just going to draw this slightly below here. So this is going to be our point at x1. So the top of that curve is going to be at f of x1. Then going back, so I'm going to attempt to draw, this is going to be pretty rough. So this is going to be my point x0, and then I'm going to have my point for x2. So again, just as a reminder, we were treating this x0 as our negative w, and we're treating x2 as our positive w. So let's find these equations. So our first equation for f of x0 is going to be equal to aw squared minus bw, because if we substituted in negative w here, negative w squared is going to become positive w squared, whereas this will be minus bw. When we substitute that in, we'll get that negative value, plus c. So that's our first function. Let's go ahead now, let's define this function, and hopefully we'll be able to appreciate this function here is just going to be equal to our constant, since that's the point where it's crossing the x-axis. The y-axis. So f of x1 will be equal to our c term. So that's our second equation. And lastly, the value of this particular function here, so this is going to be at f of x2. So this is going to substitute in positive w. So the only difference is going to be that this is going to be equal to plus bw. So that will be equal to aw squared plus bw plus c. And that's going to be equal to our third equation. So now we've got these three equations, this system of equations here, we can go ahead and solve this system of equation using any particular method. So I'm not going to go ahead and show that because I think that that's going to get even more complicated and even more crazy. And I just kind of want you to be able to understand a little bit further into the mechanics behind this function here. So I'll just let you know my solution to this particular answer. And I get my area for this entire area here that I've sketched in black. That entire area I end up getting 1/3 of the width will be equal to 2w squared plus 2wc. Okay, so what we can do then, again, we can substitute back in these values of f and we can substitute back in these values of x, and we end up with w3 for f of x0 plus 4 lots of f of x1 plus 2 lots of f of x2. So this is just for one particular part, right? So this is just for these two areas here. So this middle value, we're going to have to effectively add 4 of those middle values in there. And then we're going to have to add 2 of these values. Now, this isn't quite the end value here, and we only add 1 of this particular boundary value. So we would have to go and keep repeating and repeating and repeating that process. And so when we added up all those values, again, just to simplify, the area of this function approximated between A and B is going to be roughly W3 multiplied by the boundaries plus 2 lots of the evens. So this is my even value for x, so that's why I'm calling it my evens, plus 4 lots of my odds. And this is an odd value for x, which is why I'm calling it my odds. So let's write that. So my boundaries, that's going to be equal to my first value of x, my first value of my function plus my last value of my function. My even values here, so that's going to be equal to my f2 plus my f4 plus f6 and so on and so forth. And then I'm going to have my odds, which will be equal to f of 1 plus f of 3 plus f5 plus f of 7, all the way up until I reach my end value there. So that's where this function is derived from. So this is quite actually a complex function to derive. But now that we've reached this process, or now that we've sort of gone through this process, really all that I want you to be able to do is I want you to be able to remember and to use this function here. So in the next video, I'm going to go ahead and I'm actually going to use this function and I'll show you how we integrate or approximate an integral using Simpson's rule. See you in the next one. Have a good day. Bye, guys.